Right now, we shall prove a theorem, which is extremely important for the next chapter. So you remember we have proven a theorem that a linear map's rank plus its nullity equals the dimension of its domain. So essentially, rank nullity theorem. And then there was a corollary saying that the rank of a linear map is less than or equal to the dimension of the domain, because you remember, I mean, it's obvious corollary, because if the dimension is rank plus its nullity, both cannot be negative numbers. So then, because it's rank plus nullity, right? So equals the dimension of the domain. So it's obvious that the rank cannot be more than the dimension of the domain. Okay, now let me formulate a lemma. Then I will prove a theorem. This is extremely important statement, and we will use it to derive one of the most important things in the course. So essentially, we will show later that any homomorphism can be represented with respect to some basis, can be represented as a matrix, and any matrix is a representation of some homomorphism. So, and this is just one of the most important statements of the course. Okay, the first lemma. Under a linear map, the image of linearly dependent set of vectors is linearly dependent. So let us suppose that we started from the linearly dependent set of vectors. What does it mean? It means that if we consider such linear combination, and yeah, homomorphism which maps V into W, right? So we start from this linear combination. So, and sum of Ci's are not zeros. So this is the same as linearly, the statement that this set of vectors is linearly dependent, right? So we have proven this before. So now let us apply homomorphism to both the left and right hand sides. Okay, on the left hand side, we can use linearity, and we will get that C1H V1, C2H V2, plus and so on, plus CNH Vn. And on the right hand side, homomorphism of the zero vector is what?
Zero.
Right, zero vector again. So we have proven that. So as a result, we got that linear combination of these vectors, which are, and all these vectors are images of the vectors of the original set, right, is equal to the zero vector. And we know that not all C's, not all Ci's are zeros, right? Then correspondingly, we are getting that HV1, HVN are linearly dependent. End of the proof, right? So if we start from the linearly dependent set of vectors, we will end up after homomorphism with linearly dependent set of vectors, always. So linear dependence propagate, or is conserved under homomorphism. Now there is a question. So you remember before for the isomorphism, we said that, okay, if we start from linearly independent set of vectors under isomorphism, we will get again a linearly independent set of vectors. This is why, for example, if we started from the basis, we were getting the basis after isomorphism. Okay. Obviously, as we know, so homomorphism doesn't give us as much results as isomorphism. So it's more relaxed, right? So question is, when, if we start, under what conditions, if we start from linearly independent set of vectors, we will not lose this linear independence. So obviously, so for example, if we start from, let's say, 4-dimensional space and end up in 3-dimensional space, right? So so what happens? So we know that the images of vectors of any basis in 3-dimensional space, in this 3-dimensional space, so they will be after this linear transformation, after this homomorphism, they will be linearly dependent, right? Because we start from 3-dimensional space, end up in 2-dimensional space. So you cannot have 3 linearly independent vectors in 2-dimensional space. It's impossible, right? So as a result, I will formulate a theorem which gives an answer. Theorem. So where V is an n-dimensional vector space, these are equivalent statements. About the linear map H maps V vector space V onto vector space W. So statement number 1, H is 1-to-1. Statement number 2, H has an inverse from its range to its domain. That is a linear map. Three, null space of the homomorphism is just a trivial subspace. or which is the same, nullity of H is 0 for nullity is dimension of the null space, right? So if we have just a 0 vector, so for the trivial subspace, null space consisting of one vector, we know that by special agreement, nullity dimension is 0. Rank of the homomorphism is n. So n is the dimension of the domain of V. Okay. And 5, if beta 1, beta n is a basis for V, then H of beta 1, H of beta n is a basis for the range of the homomorphism. Okay, idea of the proof. So you remember that when we prove statements, that some set of statements is equivalent. So we either go in the loop, or here in particular, we will do it like that. We will show that these two are equivalent. And then we will show that from 1, we can go to 3, from 3 to 4, from 4 to 5. And from 5, we can go to 2. So again, we are just doing the loop of statements. So, okay, let me do this. Okay, proof. First, from 1 to 2. So let us suppose, so we need to prove if H is 1 to 1, then second statement is true, meaning H has an inverse from its range to its domain. That is a linear map. Okay, suppose that H is 1 to 1. Correspondingly, there exists inverse map which starts from the range of H and maps back to the original vector space. So let me remind you what it is. So if we starting from this vector space, and this is the resulting vector space. So if we apply our homomorphism to the whole vector space V, here we are getting H of V or range of H. Results of application of our homomorphism to the whole vector space. So then, if H is 1 to 1, then for every point, every vector in the range, we have only one vector which is mapped from here to this particular vector, right? So then, correspondingly, so we say that, okay, this is, we introduce inverse function, which is just create correspondence, right? Like that. Okay. Now, the only thing which we need to prove now, so we see that inverse exists, obviously, from the range. Now we need to prove that this is a linear map. Okay, how can one do this? So if we consider consider two vectors in the range, of our homomorphism, then we can create linear combination of them. Let us consider linear combination of them, and let us apply. So by the fact that, so we have proven that range is a subspace. So we know that there is a closure with respect to linear combination. So it's also a vector of the range. And it means that we can apply the inverse map, right? So, but now inverse map here, and I use linearity of my original H, so I can write that this is this. Now, because inverse map is well defined, so I can write that this is nothing else but H inverse combination with H. And the inverse map would give me C1 V1 plus C2 V2. But this is not exactly what I need, so I will just write it like that. So this vector V1 I can write as H inverse of H V1. And this vector V2 I can write as H inverse of H V2. So I have shown that if I will start from arbitrary linear combination of vectors from the range and apply the H inverse, I'm getting that it's equal to the same linear combination of H inverse applied to the corresponding vectors. So I have proven linearity. Okay, now, so I have proven that H inverse is a linear map, right? And then I have proven that inverse is a linear. Now, the thing is that for H inverse, so if I will start from the fact that H has an inverse, right, from the range and to the domain, and this is a linear map, so then immediately I can use the fact that inverse of the inverse is the original map, right? So I'm just inverting the approach, right? So essentially saying that inverse itself has to be one-to-one in this case. Okay, so as a result, automatically I have done also 2-to-1. Okay, now the only thing which I need to prove is just, okay, not only thing, but from 1 to 3, as I told you. So from from 1 to 3. Okay, let us do this. So it holds. So y from 1 to 3 holds. Any ideas? So why, if the homomorphism is 1 to 1, then the null space of the homomorphism is the trivial subspace? Could you tell me?
Only the zero vector from V will map to the zero vector of W.
Right, because we know for sure that any homomorphism sends the zero vector to the zero vector, right? And if it's 1 to 1, it means no other vector can be will be mapped to the zero vector, right? So that's it. So immediately we are getting that the null space is only trivial subspace. So yeah, by the way, yeah, like that, 0V. So, and then, or the same statement that nullity of the homomorphism is 0. Okay, then, because homomorphism this, right? And 1 plus 1 to 1. Okay, from 3 to 4. So we're starting from the fact that null space is a trivial subspace, or nullity is 0. But then, using rank nullity theorem, right, we are getting that rank plus nullity, which is 0, equals to the dimension of the range, right, which is n. So correspondingly, from here, we are getting that rank of the homomorphism is n. So we have got from 3 to 4. So now from 4, from the fact that rank is n, rank of the homomorphism is n. So I need to prove that if I start from the basis for V, then the image of this basis also will be a basis for the range of the homomorphism. So because rank is n, it means that dimension of the range of H is n, right? So by definition, because rank is dimension of the range. Okay, what it means? It means that in the range, basis has n vectors. So essentially, if I will show that H beta 1, H beta 2, where beta 1, beta 2 form a basis in the domain, right? So if it spans the range, then immediately I'm getting that this is a basis, right? So I need to show that this is a basis. So, but because this set of, if this, oh, nobody corrected me. Okay. If the set of n vectors spans n-dimensional space, right? So then these vectors form the basis, right? Because we have exactly n vectors which span the space, n-dimensional space. Okay, so how to show that they span the space. So let us consider some vector from the range H of V. So it belongs to the range of the homomorphism. So let us express V. Let us express corresponding V as a linear combination of basis vectors. In the domain. Okay, then correspondingly H of V just by linearity is this, right? So, but then what follows immediately that, so you see, I started from the arbitrary vector from the range, and I have got that this vector is spanned by the images of the vectors of the basis, right? And correspondingly, they form a basis, right? And finally, we need to go from 5 to 2, as I said. So here it is, from 5 to 2. So, okay. Let us assume that beta 1, beta n is a basis for V, for the domain of the homomorphism. Then correspondingly H beta 1, H beta n is a basis for the range of the homomorphism. So from here it follows that any W which belongs to the range has the unique representation with respect to these bases, right? Okay, great. Now let us define a map from range of H to V in the following way. W will be mapped to the same coordinates, but here is not a image of beta 1, but beta 1 itself. And beta n. So this belongs already to the domain, right? Because it's linear combination of vectors of the basis. So, and then it's easy to show that this is inverse, right, of W. So because if you apply H to this, so you will get exactly W, right? And it's easy to show that this inverse map is linear. So that's it. End of the proof. So we see that a linear map expresses how the structure of the domain is like that of the range. So if we have a structure in the domain, we know what happens with the structure after the map. So essentially, this is what we will use now. Okay. How to compute using this specific theorem, how one can compute a linear map. So as we said before, linear map is defined by its action on the basis. So have a look. This is why. If we start from V, which is represented with respect to some basis, then if we apply homomorphism to V using linearity, we are getting this. So in other words, in order to know how to apply a homomorphism to any vector of the domain, all we need to do, we need to express this vector with respect to some basis, and we need to know how every vector of the basis is mapped by corresponding homomorphism. So in other words, and then we just do exactly the same linear combination. So as I said before, after this map, not necessarily that these vectors will form a basis, but they will be spanning the range. So essentially, you just apply homomorphism, and then because, as we said before, if you know how your homomorphism is working on the vectors of the basis, you immediately know result of application of your homomorphism to any vector expressed with respect to this corresponding basis. You just all you need to do, you need just to compute this linear combination, and that's it. Is it clear or not? So in other words, if one knows what happens with vectors of the basis after homomorphism, or you can say H applied to this corresponding basis, you know the results of application of the homomorphism to vectors of the basis.
Professor, Could you do an example of this with real integers? I feel
Yeah,
like
I'll do right now. Yeah, I'll
okay.
do this. So if you know how to map any basis using this homomorphism, all you need to do, you need just to take the vector which belongs to your domain, express through this corresponding basis. And then you know that result of application of our homomorphism to this vector will be nothing else but the linear combination of the homomorphisms applied to the vectors of the basis. Okay, example. So boom, 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 boom. Okay, let me consider polynomial from the space of polynomials of degree 2. So in other words, and homomorphism between P2 and R1. Okay, or really, okay, R1. And it works like that, my homomorphism sense okay, let us do the following. If P of X, so is this, then homomorphism applied to P is nothing else but the following. Let's say A0 plus A1 plus A2. So this is already just a number, real number, right? Like that. Okay, how to compute, for example, yeah, so this is not very good example. Let us say like that. Yeah, let me define homomorphism like that. So I will just know that H applied to 1 is 1, H applied to X is also 1, and H applied to X squared is 1. So then these three statements, so if you know how to map vectors of the basis, so you know how to map any polynomial. So for example, H applied to the, let's say 3 plus 8x minus 10x squared. What you can do, you know that this is 3 by 1, right? So you know that 3 h of 1 plus 8 h of x minus 10 h of x squared, right? So then you know that this is 3 multiplied by 1 plus 8 multiplied by 1 minus 10 multiplied by 1, which is 3 plus 8, 11 minus 10, 1. If, for example, I would tell me please, if I would have here 2 and 3, then how how to compute it. So what I need to put here.
Well, first with the 3, you need a 1, and then with the 8, a 2, and then with the 10, a 3.
Right. So you see, if I determine just this, right, how my homomorphism acts on vectors of some basis in my domain or original vector space, I immediately know result of application of this homomorphism to any vector in the domain. Is it clear or not?
I think I would just like a little bit of clarification on something real quick. So when we first had,
let me do another example first, okay?
okay.
Maybe it will be easier then. So let us consider the homomorphism from R2 to R3. And the basis in R2 is the following: 2, 0, 1, 4. And the basis in R3 is the following: 1, 0, 0, 0, negative 2, 0. And here is 0, 1, 0, 1. Okay, now let us consider the following, that if I apply homomorphism to the first vector of the basis, I will get under H, right? So I will get, okay, let me write it differently. So result of application of the homomorphism is the vector 1, 1, 1. Okay. So how can I express it? I can express it as, with respect to this basis, I can express it as 0, 1, 0, 0, minus 1/2 of 0, negative 2, 0, plus 1, like that, right? Okay, now.
Sorry, where did you get the 1, 1, 1?
Yeah, so if you add this, so you will get exactly 1, 1, 1, right?
Yeah, but before, so how did you get the 1, 1, 1?
I'm just saying, so we know that homomorphism is defined by the action on the vectors of the basis. So I'm just essentially telling you that if you apply homomorphism to the first vector of the basis, you will get 1, 1, 1. If you apply homomorphism to the second vector of the basis, so I'm saying that you will get 1, 2, 0. So these two statements supposed to be enough to determine how homomorphism acts on any vector in R2. So this is the statement. And I'm just showing that this is really true. So for example, this you can express as minus 1. Okay. So in other words, representation with respect to the basis D, this basis of H of beta 1, this h of beta 1 is 0, -2, -1/2, sorry, 1. Another representation with respect to the basis D of the result of application of my homomorphism to the second vector of the basis is, could you tell me what is the representation?
1, -1, 0.
Yes, thank you. Okay, great. Now, with respect to any member, so any V belonging to R2, so I know that B is the basis in R2. So any vector can be represented as, for example, C1 beta 1, right? Plus C2 beta 2, right? So as a result, when I will be applying my homomorphism to this vector, using linearity, I will write this. Right? Or, in other words, C1H 20 plus C2H 14. Okay, so then I know that this is nothing else but C1 multiplied on this will be a result of with respect to the corresponding basis. Plus C2 and also representation with respect to the basis. Which I can write as, so this vector multiplied on C1 on 0 plus C2 on 1 plus second vector of the basis D multiplied on -1/2 C1 minus corresponding 1 on C2 plus the last vector of the basis. So C1 multiplied by 1 plus C2 multiplied by 0, right? So as a result, if representation of my, with respect to the basis B of my original vector was C1, C2, then representation with respect to the basis D of the homomorphism applied to this vector will be 0, 0, C1, just from here, plus C2, -1/2 C1 minus C2, and so it was this, and here it will be C1 plus 0 on C2. Is it clear or not what I have just done? For example, let's say that representation of the vector v, let's say the following vector, 4, 8, with respect to the original basis is nothing else but 1, 2, with respect to the basis b. Then representation with respect to the basis d of h of 4, 8 is nothing else but if you just substitute this c1, c2, you will get 2 minus 5 halves, 1. Is it clear or not?
I think it's clear, but for that last little part, the representation of b, the vector 4, 8 is 1, 2. Is that also just something that we're given? And then you're able to represent it in G, or
You
is that something that you compute?
here it is. We have the vector 4, 8, right? In R3, in R2, sorry. So the basis is 2, 0, 1, 4, right? So 2, 0, 1, 4, right? So what coefficients I need to use in order to represent this vector with respect to this basis? It's 1, 2, right? Is it clear or not?
Yeah, that's clear. Thank you.
Yeah, so it's here, this is here. And you were doing these problems, you are given a vector and you need to represent it with respect to some basis, right? So essentially you need to solve system of linear equations, right? You can write this as C1, C2, right? And then you will get 2C1 plus C2, and here will be 0 multiplied on C1 plus 4 multiplied by C2, right? And then you got 2C1 plus C2 equals to 4, and 4C2, 0 plus 4C2 equals to 8, right? You can solve this system of linear equations for C1, C2, and you will get exactly 1 and 2. Clear? Is it clear or not?
Yes, it's clear.
Okay.
I still had a question on the last example. However, when we did H1, the map of 1 equals 1, the map of x equals 1, and the map of x squared equals 1, was that something that you computed due to the fact that the map of P is just equal to 1 times A naught plus 1 times A1 plus
No,
1 times...
it's not necessarily. Yes, really, I used the fact that I wanted to get isomorphism to be A naught plus A1 plus A2. But then I understood that it's too easy. So, and then I said that, okay, let us forget about it, right? And then I'm just giving you how the vectors of the natural basis will be mapped, right? And then it's enough to define the homomorphism. So all you need to know about homomorphism in order to be able to apply it to any vector in the domain is how this homomorphism works on vectors of some basis. You need to choose some basis, and then you need just to figure out, doesn't matter how this homomorphism acts on these corresponding vectors of the basis. And so after that, you can apply it to any vector.
Okay, so I understand the second part, applying things to the basis in order to find...
Yeah, because of this.
But I don't understand, I guess, sometimes how you get these bases. Like how did you get h1 equals 1, hx equals 2, hx squared equals 3? Is that
No,
just
no,
something
no.
you just decided?
It's not. No, no, no. First of all, in many cases, for example, let us say that pum, 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 pum.
I feel like I just have trouble because I feel like some of these things just come from
No, 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 no.
arbitrary spaces,
No,
and
you
I
see,
can't.
you can be given a formula something like that: 3a0 plus 2a1 minus 5a2, right? For example, for the polynomial, right?
Yes.
I'm just saying that it's equivalent. Instead of giving this formula, right, specific way of how to compute the homomorphism, right? It's equivalent to give, so equivalent. This is equivalent to give just the following, that h of 1 is equal to 3, h of x is equal to 2, h of x squared is equal to -5. That's it.
Okay, I think
So
that answers.
you can give this formula, or you can give how this homomorphism acts on the corresponding vectors. Okay, so